So I'm going to be talking about event history analysis, and depending on how far we get with this, we might see some link between the earlier talk, because of course you can have multi-level event history analysis as well, but we'll see how far we get. Okay, so a little bit of an overview, what I'm going to be talking about today. First of all, just give you a few examples of where event history analysis might be used. Okay? And there's a whole range of examples from across the social sciences and beyond. Say a little bit about where event history data can be found. Okay, and talking primarily here on survey data. And then say a little bit about methods of analysis. And I'll be covering both fairly descriptive methods as well as sort of more model-based methods. Okay. And they're going to be illustrated on one particular example. We're going to be looking at the timing of a person's first partnership, and this will be using cohort studies data from one of the cohort studies that Jane will be talking about after the break. And then if we have time, further topics. I've just got one slide on that, but I'm very happy to talk around any of those, depending on what people's interests are. And as Graham said, I'm happy to take questions as we go along. It may be you ask me a question that I'm going to cover later, but that's absolutely fine. All right, so if anything isn't clear, do stop me and ask. Okay, so, well, topic of the session, what is event history analysis? So, what we're modelling here, essentially, is the timing of some kind of event. All right? So the dependent variable, outcome variable, whatever you want to call it, is a duration. Okay? It's the duration between when somebody becomes, if you like, at risk of having that particular event and when that event actually occurs to them. Okay? That's a duration. That's what we're actually modelling. Now, event history analysis, known by a lot of different names, depending what discipline you come from, these are really names for essentially the same set of techniques. Right? So if you've come from a more statistics, particularly biostatistics background, you may know these techniques as survival analysis, a very large literature on that. And the term survival comes from a focus, particularly in earlier biostatistics, on mortality. All right, so the duration of interest is the duration from when you're born to when you die. All right, and so that's where the term survival comes from. In economics, they talk a lot about duration analysis. Another term is hazard modelling, and we'll see a bit later what the hazard is. Right, it's a key quantity in event history analysis. In social science, we tend to use the term event history analysis because we think it captures better the complexity of the kind of events that can occur to an individual. There are many kinds of events that can occur over a person's life course. We'll see some examples. Births, we talked about death, marriage, divorce, and all of these events, they could happen more than once, they could codepend. All right, so the event history, I think, captures this more sort of historical perspective over a person's life. Right? But just bear in mind, it's essentially the same thing, no matter what you call it. Okay, so a few examples here. So education, you might be interested in how long somebody remains in education after the end of compulsory education. You might be interested in how long a teacher remains in the teaching profession. Okay. Economics, a lot of work there looking at the duration of employment spells or unemployment spells. So in the case of unemployment, the event there is getting a job, moving out of unemployment. All right. Whereas employment, it's leaving, it might be leaving a particular job or becoming unemployed or becoming economically inactive. A great deal of applications in demography, okay, so the timing of births, including the first, when a person first marries, and I'll be looking at an example of that in a moment, when a person divorces, okay, and then psychology, particularly in experimental designs, interest in the time that somebody responds to a particular kind of stimulus. I'll just go back to this demography example. Notice that I've said, let me click on the right one. Time to first birth from when? Now, when you're defining a duration, of course, you have to know when a person becomes at risk of having that event. Right? And in many cases, it's obvious. So if you're looking at the timing of divorce, a person becomes at risk of divorce as soon as they get married. All right? You become at risk, if we like to think positively, all right? And you become at risk of dying as soon as you're born. Right? But when does somebody become at risk of having their first child? Right? In many countries, there may be very little premarital childbearing, so you might take the time of marriage or the time of forming a co-residential union as being the start of the risk period. Okay. The term risk I'm using a lot. That again is coming particularly from the biostatistics use of these techniques where the event is usually something unpleasant like death. All right? But I will continue using the word risk even if it's something more pleasant like getting married or having a child. All right? Okay, but then so that's something you need to think about. When is it? What is a suitable origin? All right, it depends on the context. Right? In other contexts, you might want to take puberty. All right, for the timing of the first birth. Okay. All right. Now, types of event history data. In the UK, we have a great wealth of resources that we can get this data from. And in its sort of raw form, what you very often have are a series of dates. The dates when somebody becomes at risk of an event and the date that they experience the event. And from that, you can convert into a duration. Very often, this information is collected retrospectively. Okay, so in the example I'm going to be looking at, I'm looking at the age of first partnership, and in this particular cohort, people were asked at age 33 to recall events that had happened since the age of 16. So that's retrospective data. Other sources derive from panel data, where you have information on a person's current status over time, perhaps every year, and from that again you can derive the time that they spend in a particular state, a time before they have an event. And in some panel studies you actually have the two types of source together. So in the British Household Panel Survey, you have current status data going from 1991, where the panel began. So for example, you'd have people's employment status. But then the following year, 1992, people were also asked about events that had occurred before, from the age of 16. Right? And some researchers have taken a great deal of time to consolidate these two resources to form a complete history. Right? So we have complete employment histories for BHPS members, complete fertility histories, and that's also true of the cohort studies. Right? And people have generously made these data available, if you look on the archive, alongside the different studies. Right? Because if you had to do this job yourself, it is time consuming. A lot of work goes into preparing the data, but having got the data, it's very, same in a lot of statistical analysis, and most of the work goes into preparing the data. Okay. All right, so special features of these data. Why do we need to use special techniques to analyse them rather than just standard regression methods? And there are three main reasons, although the second two of these that I've highlighted in red are the most important ones. One point is that durations have got to be positive, and they also tend to be skewed. They tend to be skewed to the right. Okay, that's positively skewed. Right? And that is because you tend to have a lot of people who have the event at a very late stage. Okay, so you have this long tail to the right. That is not a major problem, because what you could do is transform the duration to get something that is more symmetrically distributed. Right? So not a major problem in its own right. These are the two major things. The most important one of these is censoring. So I've been talking about, say, divorce. Well, if you interview people at a particular point in time, many of those are still going to be married. Right? They may divorce in the future, but you've no idea if they will and when that might occur. We call those cases censored, right censored to be precise. Okay? We want to include those individuals in our analysis and include the information that they contribute up until the time that you last observed them. Because if you don't, there's two problems. One is that by excluding them, you could end up with quite a small sample size. If you only analyse those who have divorced, okay, then you're obviously ruling out all of those who are still married, and that's still quite a high percentage. And also, more importantly, you could end up with a very selective, biased sort of sample. If you're only looking at those who've divorced, particularly at younger ages, you've then got people who marry and divorce young, right? And they may be atypical of other younger people. So bias is the major problem here. So these techniques really follow people as far as you possibly can, right? The other major reason for using these techniques is that things that predict the timing of events will be varying over time themselves. So if you were looking, for example, at the timing that somebody moves house, okay, that decision is going to depend on your current circumstances. It will depend on, features of the property, how much space you've got and so on, the area that you're living in. But it will also depend on your current circumstances. A major one is your income, whether you've got children, how old those children are. Okay, these are things that change over time, and you want to bring that information into your analysis. We call these time-varying covariates. Okay. So event history analysis can bring this information in and look at how the timing of an event changes in responses to changes in some covariates or predictors. Okay, let me just go back to this censoring issue. So the censoring I described, where a person may not have experienced the event by the last time you observed them, but may in the future, that's called right censoring. And so I mentioned already that excluding them could lead to bias. An assumption that you're making here, though, by including them, is that the censoring is non-informative. Now, generally speaking, a lot of social research, that is a reasonable assumption to make, because the censoring often just depends on when the interview happens to take place. And the timing of the interview is not really related to when a person is experiencing events. That's kind of an external process to the individual. Where that will be more important is in an experimental context. I mean, let's suppose you're doing a clinical trial and you're comparing two treatments. It may be that people who, and let's say you were looking at survival as being your duration of interest. It may be that people who are particularly at high risk experience side effects to the treatment, and they may withdraw from the experiment as a result. Okay? So you're left then with a sort of selective group among those who got the treatment, and that may lead to bias when it comes to estimating the treatment effect. Okay? So it's more in these kind of clinical trial setups where this non-informative censoring is a major issue. Okay? And it's usually accepted as fairly reasonable in a lot of social research. Okay. I'm not going to show you I'm going to show you the, an equation for an event history model a bit later, but I'm going to keep it fairly simple, all right, and sort of talk a lot around it to try and explain it. A little bit of notation first of all. So for each individual, we have an event time. Okay? Alongside that, we also have a binary indicator which indicates whether or not that person experienced the event by the time you last observed them. Okay, censoring indicator, I prefer to code it this way around so that it's an event indicator. So it's 1 if they have the event and 0 if they don't. Now, if a person is right censored, so they haven't actually been observed to have the event, you do not fully observe their event time. Okay? What we actually observe is their censoring time. Okay, so and Y is just a general notation which would be the event time if a person was observed to have the event, and it would be the censoring time if they weren't. So the dependent variable is actually made up of 2 pieces of information. It's the event time plus an indicator of whether the event was actually experienced. Right? And these two people are treated differently in the analysis, the estimate, according to which category of this they're in. Okay, so that's how the censoring is brought in. Okay, now to talk about a couple of sort of key quantities, first in a descriptive way in event history analysis. And the most important one of these is the hazard function. So what that is the, loosely speaking, it's the probability of having an event at a given time point or a given interval of time. And this is the important thing, given that they haven't already had the event. All right, so it's a sort of conditional probability. And we'll look at an example of this in a moment. The survivor function is the probability that an event has not yet occurred by time t. And again, this term survival, that's coming from the biostatistics mortality kind of case, all right? Because if you haven't died, you've survived. So it's the proportion that have not yet died by a particular time point. Okay, but the term survival is stuck, so we're using it in any context, all right? But you know, it might be appropriate in some, like divorce. If you haven't divorced by a particular time point, you've survived, all right? That's the idea. But it's just it's a proportion you haven't had the event. Sometimes people will report the complement of that, just 1 minus that, and that's a proportion you have had the event by a particular time point. Okay, and just the way you might estimate these in a very descriptive way, first of all, the hazard function, what you would generally do, and what I'm describing here is a life table approach, if you're familiar with that. You group the duration into intervals, and very often the data may already be in this form because very often you don't know exactly when an event occurred. You only know that it occurred, say, within a particular month or a particular year. So often it's already in intervals. And then for each of those intervals, you report 2 things. Well, the first is the number who are at risk of having the event at the start of a particular interval. And then we've got the number of events that are observed during the interval. A third thing that we'll also have, though, is the number who are censored during the interval, the number who've sort of withdrawn from the study, or you know, it might just be the last time that we observe them. And a simple estimate then of the hazard is simply the number who have the event divided by the number who are at risk of having the event. Okay, that's the hazard function. And there are different forms of this to take into account the censoring. All right, but this is it in its simplest form. And then what we'd like to do is see how that changes over time. Once you've got the hazard function, you can estimate the survival function from it. Okay, so it's an example here. So if you've survived up to time t, that means you haven't had the event in the first interval. So it's 1 minus the hazard for the first interval. You haven't had it in the second interval either, and so on. You just multiply all these up. Okay. All right, now here's an example of just calculating these 2 descriptive measures, the hazard function and the survival function. And this data comes from the 1958 birth cohort, or the NCDS. And this particular data, they were collected at age 33. Right? So at age 33, people were asked about their partnership history. So when did they first form a co-residential union? And that would be a union lasting more than a month or more. That's how it was defined. And what I've got here is just a subsample of 500 men and women. So what we've got, and we're looking at them, their risk of forming a first partnership, going from age 16, that's what we take as the starting point, up to 33, because 33 is the age when they were all interviewed. All right. So for each of these years, we've used yearly intervals. We can look at how their chance of forming a first partnership changes with their age. That's the time variable here. So RT, that's the number you start with. Okay, and then this is the number who have the event. So we've got 9 people get married or start cohabiting between their 16th and 17th birthdays. Right? So it's before the 17th birthday because that's the next interval. Okay, and then moving on to the age 17, well, we now have 491 left. Okay, so 500 minus 9. So it's the number at risk obviously going down as people experience the event. Now, we don't have any censoring in this case because of the design of the study until we get to age 33. Okay, because everybody is followed up to age 33. But the 35 people here are people who, by the age of 33, have not yet formed their first partnership. Okay? And then from these data, we can calculate the hazard. So this is just this column divided by that one. And then the survivor function. So that's the proportion as we go through the ages who have not yet partnered. Right? They've survived partnership. That's the terminology. Okay. And right. We're going to now plot these two things. It's always very difficult to look at numbers like this in a table. Right? So we're just going to show exactly the same information graphically. 5 minutes, all right. Okay. So this is just an example of the interpretation. Let me just do the first one there. So the hazard for age 16, 0.02, so all that means is that 2% had partnered at age 16. Moving on to the next one here, the hazard at age 20 is 0.13. So this is where this sort of conditional idea comes in. So it's the 13% who were unpartnered at their 20th birthday, partnered before their 21st birthday. All right? So it's always the chance of having the event in a particular interval of time, given that you haven't already had it. All right, and here we see the plot of your hazard function, your hazard of forming a partnership. And you can see that it's increasing with age. Oops. Okay. It peaks in the 20s. That's when most people form their first partnerships. But then it starts to decline. All right. So if the people haven't had their first partnership by their early 30s for this cohort, they were fairly unlikely to do so. All right. But I should say very small numbers here. So you get some confidence intervals around there. It's really large. All right. But if you think of those 35 that we saw of the 500 who hadn't formed their first partnership at age 33, right, very unlikely to do so. Okay. They could in the future. We only observe them up to 33. All right. Okay. So the hazard function is more interesting to look at because it can go up and down. All right. So that's quite revealing. That's why it's such an important quantity. The survivor function is not very interesting because it's always going down, because it's the proportion you have not yet had the event, and it has to go down by definition. But where it might be more interesting is if you want to compare this, say, for men and women, or for different groups of some sort. All right. But in itself, it's not a particularly interesting thing to look at. All right. Now I'm running out of time, so I would just like to talk about one sort of modelling approach now. There are many ways of fitting models to event history data, and they depend on a number of things. Some of these models are not really appropriate in many social science situations because they make quite strong assumptions about the shape of the hazard function. In particular, there are methods that make assumptions that the hazard function is always increasing or always decreasing. All right. So we've just seen in our case, looking at age of first partnership, that's not going to be appropriate. So you want to be using models that are very flexible in terms of the hazard function. Another issue is how you treat time. Now, of course, in reality, an event can happen at any moment in time. All right. People can get married in any particular minute of the day. They can be born at any minute of the day. But you don't have information that precisely. You will often know, especially if you're collecting information retrospectively, you'll only have information, say, to the nearest month or the nearest year. So although the process is continuous, the actual measurement of it is discrete. So there are a lot of use of discrete time methods in event history analysis. And I'm not going to get on to talk about those today, but I think the beauty of them is that after restructuring the data, it's essentially a logistic regression. All right? So if you're familiar with that technique, then you can really just apply it to this context. Right? There's a lot of advantages to discrete time methods. I'm going to talk, though, about a continuous time method. And this is one of the most famous ones after the statistician Sir David Cox proportional hazards model. So this was developed in the 70s. It makes no assumptions at all about the shape of the hazard function, which is a major reason for its popularity. And it's a continuous time model. Okay, so this is what the model looks like. Okay, So this is the hazard function. This is actually what we're modelling here, this sort of conditional probability. All right. And what we're really interested in here is the covariate effects. So as usual in a regression model, you've got some coefficients that you're going to estimate. And often people will write it in this form. So you take logarithms, and this then starts to look a bit more like a regression model that you might be familiar with. All right. So again, this is the bit of interest. It's the effects of the covariates. They could be time varying. We can add those in. And this plays the role of the intercept. Okay, it's called the baseline hazard. But the important thing about it, unlike the intercept in the usual regression models, is that it depends on time. Right? So that's capturing how your chance of having the event is changing over time. That's captured by this here. Okay. A little bit on interpretation. Okay. Let me actually just move straight to an example. So it's always easier to explain interpretation then. This is a very simple model in that we've only allowed for gender effects here. All right, so we're looking at how the timing of first partnership differs for men and women. Okay, and you can see first of all that this is significant. This is, if you're familiar with SPSS, then you'll recognise tables like this. Okay, but you can do this analysis in any statistics package, and I'm happy to talk about that in the questions. This is our p-value. So there's a significant gender difference in the timing of first partnerships. All right. And we can interpret this number here. What we do is we just take the exponential of this coefficient here. So it's about 1.5. So what that says is that any particular age, the hazard of partnering is about 1.5 times higher for women than it is for men. And what that means, if you've got a higher hazard, what that means is that you experience the event earlier. Right? So women are partnering at an earlier age than men. Okay? But what we've done so far is assumed that the gender difference in the hazard is exactly the same at every age. And that's called the proportional hazard assumption, which is straightforward to relax. All right? Because what you find if you do that is that there's a big gender difference at the young ages because women are partnering earlier. But as you get to the older ages, men have caught up and you've got very little difference at all. Now I'm going to move on to this discrete time method that I talked about, which boils down to logistic regression. Right? So how many people are familiar with logistic regression? Okay, quite a few hands. All right. So really, all we're going to do is sort of restructure the data into a particular form. Then you can apply logistic regression. Okay, which is obviously very attractive because you don't have to then learn a new technique. But there are a lot of other advantages to it. One is that it really is taking into account that often these measurements are in discrete time, so the model reflects that. It's very straightforward to allow for these non-proportional hazards, and it's also more easily extendable to cover more complex situations, such as having events that are occurring more than once to an individual. And what that then gives you is a multi-level event history analysis. Right? 'Cause you can think of then having repeated episodes within a individual. All right. Okay, well let me just tell you then, this is the important bit, how you restructure the data. So we've got two individuals here. Okay, this is the time that they have the event or the time that they were censored if they haven't yet had the event. So this person formed their first partnership at age 21, and we know they formed the partnership because this is our censoring indicator, which is equal to 1 for this person. Right, so they had the event. This person has not yet formed their first partnership at age 33. All right, so they are censored. What we then do is for each individual, we expand that information into a series of records, one for every age, one for every year, from age 16 up until the last point we observe them, or when they have the event. So the first person then is going to have records going from age 16 all the way up to age 21. And then we have this binary indicator which tells us whether or not they had the event during that interval. So this person, we know they didn't have the event until age 21, so we know they didn't have it when they were 16, nor did they have it at 17, and so on. So they didn't have it until age 21. So you have a string of zeros followed by a 1. Whereas this second individual, they never had formed a first partnership, well, certainly not by the age of 33. And so you'll have records going all the way up from 16 to 33, and their responses would be a string of zeros because it didn't have the event in any of those years. All right? So the pattern this is now going to be our response variable, is always really the same. It's either a string of zeros followed by a 1 if they have the event, or just a string of zeros if they were censored. All right? So that's the restructuring of the data that needs to be done. And then we analyze these data using logistic regression with this as our binary outcome variable. And what we're going to do to allow the chance of having the event depend on age is to include in our model this variable here in some form. If we just include it as it is, then we're assuming a linear effect of age, right? which we know is not going to be reasonable, because we looked at that hazard function, you could see that it was going up and then down again, so it's not linear. But you can include some function to allow for that non-linearity, and that's what we'll do. Okay, so that's the logistic regression model. Okay, so here is we're going to analyse the same data, make it a little bit more interesting though. We've got a time-varying covariate. And this is an indicator of whether, at a particular age, a person is in full-time education. Because you might expect that while a person is in education, they might not form their first partnership. They may delay that until after they've left education. And we've now got to specify the form of the hazard function in our model. And it's really important to always look at that plot initially to give you some clues as to what might be a suitable form. Right? So one approach, we call it a step function, and that's just a fancy way of saying that we fit a dummy variable for every age. So we're treating age like a categorical variable. And that's a good place to start, because that really gives you an idea of what the shape is. And then, having looked at that, you might simplify it in some way and represent it in a more parsimonious way. All right, so this is the step function. So it looks pretty horrendous. So this is again from SPSS, and all this is a logistic regression, having restructured the data. So we'll go all the way down to our estimates of interest. So this is the gender effect. Okay, and it's actually pretty similar to what we had before in the Cox proportional hazards model. And then this is the effect of being in full-time education. So being in full-time education reduces a person's chance of forming a partnership. Okay? Well, we know that women have a higher chance at a particular age. They partner earlier. What are all these here? These are the dummy variables for age. And we've taken age 16, the first age, as the reference category. So this is the effect for age 17, age 18, and all the way up to age 33. And what you can see, if you look at the pattern of these, then it really follows that plot that we saw at the beginning. Okay, so you can see that the hazard is increasing, the numbers are getting bigger, a few blips, but generally getting bigger, and then they start to go down again as we reach these older ages. But look at the standard errors, how big they are. We've got very few people left at that point to be able to really estimate this very well. Okay, but you can see it's going up and down. So maybe a simpler way of capturing this would actually just to fit a quadratic, right? So we'd have age in there and then age squared, right? And that's what we've done here. And if you were to compare the coefficients of interest, gender and education, you see they were very, very similar to what we had in that more complex model. Right? So this seems to do the job fairly well of capturing the shape of the hazard function. All right. Okay. So let me just finish really by talking about non-proportional hazards. Right? So we've assumed that the effects of, they say, gender are the same at every age. And it's important always to test this. And in discrete time, allowing for non-proportional effects is essentially just fitting an interaction between the time variable and the variable that you think has a non-proportional effect. Right? But let me just show you this graphically, show you what this means in practice. This is an example of the proportional hazards model. Right? And I always look at this, it's a bit of an optical illusion. But what you've got on the left-hand side here, the log odds of partnering, and then we've got age, and then we've got the men are in blue and the women in green. What's important is to look at the distance between the blue and the green dot at every age. And what you see if you do that is that the distance is exactly the same, right? So it's best to just sort of draw lines, all right? So do that. You see it's actually the same. All right? It doesn't look like it when you first look at this graph. Right. But what that's saying then is that women are more likely to form a partnership at any given age than men, and that gap is the same for every age. Now, if we allow for the non-proportional hazards, okay, we get this slight shift. So we've got the women, the very similar shape for both men and women, but the women are shifted back, and that's reflecting the fact that women are partnering earlier than men. So this is what I meant by the catch-up here. So by this point here, so sort of mid-20s, men and women actually are very similar in terms of their hazards of first partnering. Okay, so the action, if you like, in terms of gender, is all at the younger ages. That's where the differences occur. All right. And I think just end by just saying about further topics that we can look at, repeated events. And all these topics are a lot easier to look at within this discrete time framework. So I'll leave you to look at those yourselves on the website. I think it's important, as Kelvin did, to say a little bit about where next, where can you find some resources. Okay, and on our online course, we don't yet have anything on event history analysis. That is something we hope to remedy over the next year. But for the moment, now in terms of the discrete time approach, this I would recommend as being the place you start. Right. It's an educational example. It's looking at the length of time teachers stay in the profession. Really clearly written paper. The same authors have written a book on applied longitudinal analysis, and half of that book is about the discrete time approach that I've talked about in about 5 minutes. Right. And they really go through at a very leisurely pace, and it's extremely clear. Another book I would recommend that covers a broader range of models would be a book by Hans-Peter Blossfeld and Gert Rohr. So they're the sociologists. So it's written for a social science audience, and the book has been around for a while, but more recently it's been written around Stata. Right, so if you're a Stata user, well, I'll publicise one of my own pieces on this. So this is one of the NCRM methodological reviews. That was written in 2005. And then this is just a paper that covers some of the more advanced topics that I mentioned. Okay, so quite a lot of resources out there, particularly on discrete time approaches.